Every star you can see tonight is doing exactly one thing, and it has been doing it since before there were people to look up. It is holding itself up. A star is an enormous weight of gas trying to fall into its own center. The only thing stopping it is the heat coming out of the middle. Take the heat away and the whole thing falls in. That is the entire life of a star, and the entire death of one. A very long argument between weight and heat, which weight eventually wins in every single case without exception. Nothing in the sky is permanent. The difference between the stars is not whether they end, but how long they take and how loud they are about it. Some take 10 million years and finish in a second. Some will still be shining when the universe is 1,000 times older than it is now. Tonight we are going to follow that ending, in order. What happens in the middle? What comes off the outside? What is left over? And what the sky looks like when there is nothing left to look at. Nothing here is a prediction about anybody. All of it is far away and slow. A star only ever runs out of fuel in one small part of itself. This is the fact that makes all the others make sense, and it is almost always left out. A star does not use itself up the way a candle does. Fusion only happens where the pressure and the temperature are high enough, and that is a small region right in the center. In the Sun, that region is about 1/4 of the radius and holds a bit over 1/3 of the mass. Everything outside it is fuel that will never be touched. So when we say a star runs out of hydrogen, we do not mean the star has no hydrogen left. The Sun will end its main life with most of its hydrogen still sitting there, out where it is too cool and too loose to do anything. It runs out in the middle, and the middle is the only part that was ever holding the rest up. The material outside does not mix in. There is no stirring. In a star like the Sun, the outer layers move heat by convection, but the core stays separate, and the ash of one reaction stays where it was made. We know the layout because of sound. The Sun rings, very quietly, from turbulence in its own surface, and those vibrations travel through the inside and come back. Reading them tells us where the layers are, how fast they turn, and how deep the churning goes. The technique is called helioseismology, and it has been done from spacecraft since the 1990s. A star is not a burning object. It is a thing with a small hot engine and an enormous amount of dead weight sitting on top of it. The biggest stars have the shortest lives. The intuition is that more fuel lasts longer. For stars, it is the exact opposite, and it is not a small effect. A star 10 times the mass of the Sun has 10 times the fuel. It also has vastly more weight pressing on its center, and the reaction rate climbs very steeply with temperature. That star gets through its life about 1,000 times faster. It lives around 20 million years instead of 10 billion. At the top end, it is stranger still. The most massive stars known, around 100 times the Sun, last a few million years. That is less time than there have been recognizable human ancestors on Earth. Every one of the great bright blue stars in the sky is younger than the grasslands. At the bottom end, it goes the other way just as hard. A star 1/10 the mass of the Sun is cool, dim, and extremely careful with what it has. Its lifetime runs into the trillions of years. The brightness is what gives it away. A star's output rises roughly as the 3rd or 4th power of its mass, so 10 times the mass is thousands of times the light. The fuel is spent at that rate. We can check this by looking at clusters, where all the stars formed at about the same time. In an old cluster, the bright blue ones are simply gone, and the age of the cluster can be read from where the missing part of the sequence begins. Bright is the same thing as brief. No small star has ever died. There is a whole class of star that has never once finished. Not rarely, never. Red dwarfs are the smallest things that count as stars, from about 8% of the Sun's mass up to about half. They are the most common object of their kind in the galaxy, by a wide margin. Something like 3 out of every 4 stars is one of these. They are also almost entirely convective. The whole body of the star churns slowly from center to surface and back, so unlike the Sun, the fuel out at the edge does eventually get carried into the middle. A red dwarf can use nearly all of itself, not a third of itself. Combine that with a very low output, and the numbers get strange. Calculations give lifetimes from hundreds of billions of years up to something like 10 trillion for the smallest ones. The universe is 13.8 billion years old. That is not a rounding error against 10 trillion. It is less than 1 part in 700. So every red dwarf that has ever formed anywhere is still burning. They have not reached middle age. The first one to run out will do so long after every star like the Sun has finished and cooled. This one is worth naming honestly. It is a calculation, not an observation. There is nothing to check it against because the event has never happened. What we can check is the physics of small stars and the way they mix, and both are well tested. The Sun will swallow 2 planets and then quietly stop. We said in the episode about the Sun that it will never explode, and that is still true. It is not massive enough. What it will do instead takes about 1 billion years and is mostly slow. When the hydrogen in the core runs out, the core contracts and gets hotter, and that heat pushes the outside of the star outwards. The Sun becomes a red giant. Red because the surface, spread over an enormous area, is cooler than it is now. Giant because it will reach out past where Mercury and Venus are. Those 2 planets go. That part is not in doubt. Earth is genuinely unsettled. The reason is not the size of the Sun. It is that by then the Sun will have blown away a substantial part of its own mass, and a lighter Sun holds its planets less tightly, so all the orbits move outwards. Whether Earth moves out faster than the surface comes in depends on numbers that different models handle differently. Papers have come down on both sides. It does not matter much either way. The oceans will have gone about 1 billion years before that, from the slow brightening that is happening now. Then the outer layers drift off. Not blown, drifted, at a few tens of kilometers per second, which is slow for this subject. The core is left behind, naked and very hot. We are confident about all of it, because we can see other stars at every stage of it, right now, at different distances. Nobody is waiting 5 billion years. The whole sequence is laid out in the sky simultaneously. A planetary nebula has nothing to do with planets. The shells of gas thrown off by dying stars are the most photographed objects in astronomy. Rings, hourglasses, butterflies, glowing shells with a small white point in the middle. They are called planetary nebulae, and there are no planets involved at any stage. The name is from William Herschel in the 1780s. Through the telescopes of the time, a small, round, greenish disk looked like the disk of Uranus, which he had found himself a few years earlier. The name stuck, long after everybody knew it was wrong. Astronomy is full of these. What they actually are is the outside of a star. lit from within. The exposed core left behind is extremely hot, tens of thousands of degrees, and it floods the departing gas with ultraviolet light. The gas glows in specific colors depending on what is in it. Oxygen gives the green, hydrogen gives the red. The important part is how short they last. The gas keeps expanding and thins out, and the whole display fades within about 10,000 to 20,000 years. In the life of a star, that is an instant. It is the reason there are only a few thousand of them known in the entire galaxy, while there are hundreds of billions of stars. At any given moment, almost nobody is doing it. Every one of those photographs is a star, in the middle of a step it will finish, before recorded history could have been written twice. What is left is an ember that has not finished cooling anywhere. The core that is left behind is not a star. It makes no energy at all. Nothing is fusing inside it. It is simply an object that is extremely hot and has nothing to do but cool down. It is also astonishingly small. Take something with the mass of the sun and squeeze it to roughly the size of Earth. A piece, the size of a sugar cube from inside one, weighs about a ton. What holds it up is not heat, which is why it can stop making heat and still not collapse. It is a rule about how closely electrons can be packed together, and that rule does not care about temperature at all. It also gives the object a hard limit. Above about 1 4/10 of the sun's mass, the rule fails, and the thing collapses further, which is one of the cleanest numbers in the whole subject. Then it cools, and it cools very slowly, because it is small and has almost no surface to radiate from. Calculations put the time to go completely dark at something on the order of 1,000 trillion years, so there is no such thing, yet, as a burnt-out star. Not one. The universe has not been running long enough for the first white dwarf to finish. The coldest ones found so far are still around 3,000 degrees, and their ages, read from that temperature, come out near the age of the galaxy itself. They are used as a clock for exactly this reason. Everything that has ever died out there is still warm. A big star dies at the moment. It makes iron. Massive stars do not stop at helium. When one fuel runs out, the core squeezes, gets hotter, and starts on the ash of the last round. Hydrogen to helium. Helium to carbon and oxygen. Then neon, then oxygen, then silicon. Each stage is hotter, faster, and shorter than the one before. In a star around 20 times the sun, hydrogen lasts several million years. Helium lasts a few 100,000. Carbon lasts about 1,000. Oxygen lasts about a year. Silicon lasts a day. What silicon makes is iron. And iron is where the whole process stops paying. Up to iron, sticking nuclei together releases energy. Past iron, it costs energy. An iron core cannot hold anything up. It just sits there accumulating, inert, while the shells above it keep dumping more iron onto it. The star at that moment looks completely normal from outside. It has been bright and blue or bright and red for millions of years, and it is still bright. Nothing on the surface knows. We know the sequence from the wreckage. The material thrown out of exploded stars, measured in remnants and in the light of the explosions themselves, contains exactly the elements this latter predicts, in close to the predicted amounts. Silicon, sulfur, calcium, nickel, and iron, all in the right places. The star spends 10 million years making the one thing that will finish it. The collapse takes less than a second. When the iron core passes about 1 4/10 solar masses, the support gives out, and the middle of the star falls. It falls from something around the size of Earth to something around 20 kilometers across. It does this in well under a second, and the inner part reaches a quarter of the speed of light on the way in. Then it hits itself. The center becomes so dense that it stops being compressible, and the material still falling in bounces off it. That bounce, helped along by everything described in the next fact, drives a shock wave back outwards. Here is the part that is hard to picture. The star is enormous. The shock has to travel from the middle all the way out through hundreds of thousands or millions of kilometers of the star's own body before anything is visible from outside. Depending on the size of the star, that takes hours, sometimes most of a day. For that whole time the star is already destroyed and still looks completely ordinary. The surface is shining exactly as it did the day before. Then the shock arrives, the surface is lifted off, and the object brightens by a factor of billions in a few hours. The delay is not a theory. It was measured in 1987, when a star died in a nearby galaxy, and two different kinds of signal arrived from it at two different times, which is the subject of the next fact. Almost none of a supernova comes out as light. A supernova is the brightest thing most people have ever heard of. For a few weeks, one star can outshine the entire galaxy it sits in. That display is about 1% of the energy, less in most estimates. The overwhelming majority leaves as neutrinos. When the core collapses, protons and electrons are pressed together into neutrons, and every one of those reactions releases a neutrino. Something like 10 to the 58th of them come out in about 10 seconds. Neutrinos barely interact with anything, so they pass straight out through the entire body of the dying star at nearly the speed of light, while the shock wave is still grinding its way outwards. Which means they arrive first. On the 23rd of February, 1987, 3 detectors in Japan, the United States, and Russia recorded a total of about 24 neutrino events within roughly 13 seconds of each other. Around 3 hours later, astronomers in the southern hemisphere saw a new star in the Large Magellanic Cloud, 168,000 light-years away. 24 particles. That is what a nearby exploding star delivers to instruments the size of a swimming pool, and it was enough to confirm the whole picture of what happens inside. It remains the only supernova whose neutrinos anybody has ever caught. There are detectors on watch for the next one, connected to an alert system, because the neutrinos give a few hours of warning before there is anything to point a telescope at. A spoonful of what is left weighs as much as a mountain. If what remains after the collapse is under about 2 or 3 solar masses, it settles as a neutron star. Take 1.5 times the mass of the Sun, put it in a ball 20 kilometers across, about the size of a city. That is a density comparable to an atomic nucleus, and a teaspoon of it would weigh something like 1 billion tons. The other thing that happens is spin. Anything that shrinks spins up, the same way a skater does by pulling their arms in, and this is a shrink by a factor of tens of thousands. A core turning once a month comes out turning several times a second. The fastest one found so far completes 716 turns per second. That is an object the size of a city, heavier than the Sun, spinning faster than a kitchen blender. Many of them fire a beam out along a magnetic axis, and if that beam sweeps past Earth, we receive a pulse each time it comes round. They are called pulsars, and they are among the steadiest clocks in existence. The first one was found in 1967 by Jocelyn Bell Burnell, who noticed a repeating signal in a chart recording from a radio telescope she had helped build. The signal was so regular that the group half-seriously labeled it LGM-1 for Little Green Men, until a second one turned up in another part of the sky and settled the question. If the leftover is heavier than about 3 solar masses, nothing known stops it, and it goes on collapsing into a black hole. That is a whole subject of its own, and not for tonight. Some of the gold in the world was made by 2 dead stars colliding. Ordinary fusion in stars cannot make gold. Past iron, sticking nuclei together takes energy rather than giving it. So the heavy elements have to be built somewhere with an enormous supply of loose neutrons and no time to waste. For decades, the sites for that were argued about. On the 17th of August 2017, one of them was watched directly. Detectors on 2 continents felt a gravitational wave, a ripple in space, that lasted about 100 seconds and had the signature of 2 very dense objects spiraling together. 2 seconds later, a satellite recorded a short burst of gamma rays from the same direction. Within 11 hours, telescopes found a new point of light in a galaxy 130 million light-years away. That point of light then behaved exactly as predicted for freshly made heavy elements. It faded from blue to red over days as a cloud of newly built atoms expanded and cooled. Estimates of the amount of gold produced in that single event run to several times the mass of Earth. The honest part is what remains open. That mergers make these elements is now observed. What fraction of all the gold and platinum in the universe comes from mergers, and what fraction from rare kinds of exploding star, is still an active argument, and papers disagree. The metal in a wedding ring was made somewhere violent. Which kind of violent is not fully settled. A star once appeared in daylight, and somebody wrote it down. On the 4th of July, 1054, court astronomers in China recorded a guest star in the constellation we call Taurus. Their records are specific in a way that is very useful 900 years later. It was visible in daylight for 23 days. It remained visible at night for 653 days, and then it faded and was gone. Japanese records mention it too, and there is a probable reference in an Arabic medical text. In the same part of the sky, there is now a cloud of shredded gas about 11 light-years across, still expanding at around 1,500 kilometers per second. Wind the expansion backwards, and it converges on a point at a date close to 1054. At the center of that cloud is a neutron star turning 30 times a second, and it is still feeding the cloud energy 970 years later. The whole nebula glows because of it. That is the cleanest connection in this episode, a line written by an official in a court that has been gone for centuries, and an object in a telescope tonight, and they are the same event, and the arithmetic joins them without any help. One of the bright stars of winter will go, and nobody can say when. The orange one on the shoulder of Orion is a red supergiant. It has already left the main part of its life, and it is near the end. Almost every number about it is uncertain, and this is worth stating plainly. It is close enough that its distance is hard to measure well, because the star is not a point, and its surface boils in enormous patches that move the apparent center around. Estimates run from roughly 400 to 700 light-years, and the mass and the timing depend on which is right. The best that can honestly be said is that it will explode as a supernova sometime within the next 100,000 years or so. That is tomorrow in one sense, and never in any sense that concerns anybody alive. In late 2019, it dimmed noticeably, by more than half its usual brightness, and stayed dim for months. It was widely reported as a possible warning. Observations with the Very Large Telescope, published in 2021, explained it. The star had thrown off a cloud of gas that condensed into dust in front of it, over a cooler patch on its surface. Not a countdown. Weather. When it does go, it will be roughly as bright as a half moon, visible in daylight for weeks, and completely harmless at that distance. Then Orion will be missing a shoulder and stay that way. The sky empties slowly, and the last lights will be the smallest. New stars are still being made. There is enough gas left in this galaxy for that to continue for a long time, though the rate is a small fraction of what it was 10 billion years ago. The best years for star formation in the universe are already behind it. Eventually, the gas runs low. The big stars go first, as they always do, in millions of years. The ones like the Sun follow over billions. And then what is left in the sky for an almost unimaginable stretch of time is the smallest, dimmest, most economical stars, doing what they do now, very slowly, with nothing else around them. The last of them are expected to still be shining when the universe is around 100 trillion years old. That is roughly 7,000 times its present age. Everything that has happened so far, including all of it, would sit in the first 1,000th of that story. After that, the sky has only cooling remnants in it, and they take longer still. None of this is a warning about anything. The numbers are so large that they stop being about time in any sense a person uses the word. It is simply the shape of the thing. The sky is a slow fire that was lit, is burning unevenly, and has an end that is further away than the beginning is behind. That is 14 of them. There is one thing worth saying before you go, and it is the only part of this that is about you. Everything described tonight is where you came from. Hydrogen and helium are from the beginning of the universe. Everything else was assembled inside a star and put back out again by one of the endings we have just been through. The carbon in your body came from stars that swelled, cooled, and drifted their outer layers away. The oxygen and the iron came from ones that collapsed in a second. The small amount of heavier metal came from something rarer and more violent still. The sun is not first generation. It is built out of material that has been through at least one round of this, and the proof is sitting in it. A star made purely at the beginning of the universe would have almost nothing in it heavier than helium, and the sun has a whole periodic table. So the sky is not a collection of permanent objects. It is a slow process of making the heavy things out of the light ones, one star at a time, and the process is what produced the ground you are lying on and the person lying on it. None of it is urgent. All of it is very far away. Sleep well.